Good morning, class. This is a continuation of the lesson we had yesterday, and we stopped at a point where we had derived the formula for arc length. L is equal to pi r theta over 180 degrees. And this one, we arrived at this formula by defining the arc length of a circle for any given angle. That means if we are given an angle in any circle, we are able to calculate that arc length without using any other formula that we derived yesterday. So this will be the general formula that will guide you in any calculation of lengths, arc lengths of a circle. So if you look at, we want to look at an example on the same. Calculate the arc length L, which subtends an angle of 60 degrees at the center of a circle of radius 7 meters. So if you look at that, we have said that the angle at the center is the one that is subtended by that particular arc length. So the bigger the arc length, the bigger the angle. So we have L is equal to pi r theta over 180, where r is the radius of the circle and theta is the angle subtended. So we substitute. There we get 22 over 7, which is pi. 7 is the radius, and 60 over 180 degrees. So when you calculate that, you get 7.33 meters. Now I have a dot on top of the last 3. It means that the division is recurring. It is not it is infinite. So we put a dot on the last digit if the division is recurring, so that this one indicates that as we can continue dividing and dividing and dividing infinitely without coming to an end. That's why it is 7.33 meters, but the last digit has a dot on top of it, meaning that the division is recurring. Let's look at another example on the same. Look at another example. So you can see now we have another example, but this is a more advanced one from what we did earlier. Now this question asks us to find now the angle subtended by this particular arc length. So what we do, you first of all state the general formula, which is L is equal to pi r theta over 180 degrees. So you do the first basic substitution on what you have been given. In this question, you have been given arc length, which is L. You have been given the radius, which is 10.5. So what you don't know is theta. So we shall do the first basic substitution. So that is what you do first as step number 1. 22 over 7 times 10.5 times theta over 180 is equal to 33. So you do simplification on this. You can multiply and then you finally divide. Let's see what comes out of it. So 15.4 over 36 is equal to 33. So you work out the value of theta. You eliminate the denominator. You multiply both sides by 36. And at the same time, you eliminate 15 by dividing by. So you multiply by the reciprocal of 15.4 over 36. So that will be 36 over 15.4 divide by 15.4 by 36.1 by 36.1 by 15.41 by 15.41. So you get theta is equal to, you multiply that, so you get roughly the angle you are getting is 77.14 degrees. That is the angle subtended by this arc length at the center of the circle. So you can now use this formula to get, we can also get radius if we are given theta and we are given L. So this is a general formula that will guide you to get any of the unknowns in this particular subtopic. So finally, let's look at the last example that will calculate R. So look at this question, class. An arc length L is equal to 42 centimeters subtends an angle of 85 degrees in a circle of radius R. Calculate the radius of the circle, correct 2 decimal points. That is the question that now will give us the calculation of the radius, but the general formula remains the same. So let's work it. So this is the diagram that will help us solve R. Find R. R is the unknown, so we use the general formula for our solution. L is equal to pi r theta over 180 degrees. So we do the first basic substitution of what we know. So we get 22 over 7 times r times 85 over 180 is equal to 42. This is the first basic substitution that will lead us into getting the value of r. So we do the basic multiplication so that we are able to get r. So we get if you multiply 22 by 85, then you divide by 7 times 180, you get approximately 1.48 theta, 1.48 r. So we now get the value of r, and to get the value of r, we divide throughout by 1.48. Divide throughout by 1.48, and that should be able to give you, if you work it out, should be able to obtain should be able to obtain approximately 28.38. Remember our question said we give our answer correct to 2 decimal points. So you can see we have looked at the 3 examples. The first example was on calculation of L. The second example was on the calculation of theta. And the third example now is on the calculation of R, which we have done successfully. So that formula guides us in any other question that will be related to arc lengths or circles. So we want to move ahead and look at just applications on what we have done before now we go to another subtopic. Now I want us to do this exercise in relation to what we have learned. Exercise 1. That is the composite figure. We have been told to find its perimeter. These are the informations that are given in the question. Meaning that the straight edges that are included in the figure are equal. Remember these mathematical symbols, what we said they mean yesterday is that if we have such a mathematical symbol, it means that the edges are equal. Now, additional information we are given. So we are given that the distance from this point to that point is 6, and the dimension from this point to that point is 12, meaning that if this one is 6, it means that the remaining shared length, this one and that one, is also 6. So it means therefore that this will be 3. And this will be 3. Similarly, this one we are also given as 12, meaning that this is also 3, this is 3, this one will be 3, 3, 3, and this is 3. So you can see the only remaining length that we don't know is this one here. And this one will be calculated. If you look at this one forms like this one forms a semicircle. And since it is a semicircle, we can find this arc length by the use of the formula C is equal to pi d over 2. From what we learned yesterday, we saw that the circumference of a semicircle is given by pi d, where d is the diameter, and we are now dividing the circumference by 2 to get the circumference of the semicircle. But if you look at this figure, there are 4 such similar semicircles. Why? This one is also similar to this. This one is also a similar one. And the lower one is also similar to the rest. So if there are 4 and one is pi d over 2, then to get the curved length of the 4 semicircles will multiply by 4. But first of all, let's find the curved length of the first semicircle. So 22 over 7. 22 over 7 times 6 over 2. Why is 6 over 2? Because 6 is the diameter. (22) times 3 over 7, because this is 1, this one is 3. So you get C is equal to I've given my answer correct to 3 decimal points for the start, because I'm still to work on it so that I get the exact area that I can now approximate to 2 decimal points. So this is the curved length of 1, and there are 4. So we start the addition of what we said. If we are asked to find the perimeter, you add all the edges round back to where you started. Let's see how we do that. This is point A. So we add all the way from A, B, C, and that one you move round like this. From C to D, D to E, E to F, we move round like that. F to G, G to H, H to I, we move round like that. I to J, J to K, K, we move round like that to L, then we go from L back to A. That will be the perimeter of that composite figure. So let's look at how we want to add that. So class, when you add all this, we get our perimeter as 61.71. In that question, we were not given units, so you just leave it the way it is, because it's just given dimensions, 12 and 6 and 12. So you just leave it the same way if you are not given dimensions. Let's look at the last example on that. So you look at this figure, and we have been asked to calculate the perimeter of such a figure. So what you do, you interpret the information that can give you a figure that looks like an arc length, which you can use the formula that we have developed earlier on to compute. So if you look at this figure, the lower part is a semicircle. This part also is a semicircle. The upper part is also a semicircle. It's also a semicircle, which we can use now use the formula that we have developed to calculate the perimeter of the figure. The information given That is the information given. And from this information, we can interpret several informations from it. These mathematical symbols, we have once again repeated that if you see these mathematical symbols, it means that the lengths are equal. So it means that this is also that is also 10 units. So I can find the area of this semicircle, no, not the area, sorry, the perimeter of this semicircle, and also the perimeter of this semicircle. And therefore, if this is 10 and this is 10, it means that the diameter of the whole semicircle, the upper one, is 10 plus 10, which is 20. So I'll get the perimeters of each semicircle, then I do what we call summation. So let's find the perimeter of the first semicircle. Use the formula pi d over 2 because it is diameter. So you get 62, so it gives you 62.86. So the circumference of the larger semicircle is 62.86. Let's work out the lower ones because they are the same. And we will multiply by 2. This is 10 and this is 10. So when we get that, we multiply by 2. So I'm multiplying by 2 because they are similar. This is 10, this is 10. Otherwise, if they were not similar, you work out individual perimeters, then you do summation. So you get 22 over 7 multiply by 10. So for the perimeter of the lower semicircle here, this plus that, the length is 31.43. And the other one was 60. 62.86. The other one was 62.86. So you do summation. Let's now start the journey of adding. If I have this point as A, this point as B, and that point as C. So I add A to B, B to C, then C go round back to A. C to A is 62.86. Then AB up to C is 31.43. So we get perimeter of the figure. So when you add that, you get you get 94.29 units. They don't have dimensions, so they are just units. So that is how you work out lengths of composite figures like this using the formula that we derived yesterday. And you can continue. Many more examples can be given on the same, but the formula will remain just the same formula. So we want to move on to another subtopic in the same. Area of circles and sectors. Now, what is area? So when we define area, we say it is the plane occupied by a surface. Now, a surface can be the floor we are standing on is a surface, and it is defined also as a plane. So it has dimensions. The dimensions we are talking about will be what we are measuring. Like in this particular class, we can measure the length of the class, we can measure the width of the class, and those are now the dimensions that define the class. So when we talk about area, it's just a plane. And that plane is what we say a surface. So when we are able to calculate the total area of the class, then we shall have gotten what we call the area of the plane, which is basically the class. So for example, if I have that one as my plane, and this plane defines the figure, which is a rectangle, and be A, the plane is defined by the rectangle A, B, C, D. In this particular plane, I have length and I have width. So to get the area of that plane, I'll say if you multiply length by width, you will get the area of the plane. So the shaded region will be basically area defined by this plane A, B, C, D. Likewise, if this is the area of that plane, we can also get the area of other plane figures. And remember, in year 8, we defined several plane figures that we have in life. Examples of the plane figures we define in life are as 1, these were the examples of plane figures that we defined. And we said it's a rectangle, triangle, circle. And basically we are talking of all polygons. Remember, when we talk about all polygons, the circle is a polygon, a triangle is a polygon, a rectangle is a polygon. So when I talk about generally all polygons, it means that anything that is defined as a plane will qualify to be called a polygon. And a polygon has sides, so it depends on how many number of sides we are talking about to define a particular plane. For example, a rectangle is a 4-sided polygon. A triangle is a 3-sided polygon. A circle has infinite number of sides, and it qualifies to be called a polygon. So any figure that we can define as a plane qualifies to be called a polygon. And those are the examples of planes we define. So if area of a plane is defined by area is equal to L times W, then it means that the qualification of area is a multiplicative operation, where we multiply two edges of a polygon and we get the area. And this will now be the guiding concept that we are going to use even in deriving the area of a circle, even deriving the area of a triangle, and deriving the area of any polygon that we have in life. And I've said that any figure that satisfies to be called a plane is therefore defined as a polygon. Recall that in our year 8 we discussed that the area of a circle is given by pi r squared, where r is the radius of the circle. So if this is true, then for any given circle of any given radius, we can be able to calculate the area of that particular circle. So you will recall this formula. So for example, if we had this particular circle with a radius r is equal to, let's say, 7 centimeters, then we can calculate its area simply by saying A is equal to area is equal to 22/7 times 7 times 7. (154 centimeters square is the area of that particular circle. And from there, from the area of a circle, we can now develop what we call the area of a sector. That is my main concern this morning, because this is what we want to derive, to arrive at. What is a sector? What is a sector of a circle? So a sector is defined just simply as a portion of a circle as you are going to see we are going to demarcate that portion, and the portion we demarcate is what we call a sector. So class, in the diagram below, the shaded region satisfies the definition we have given above, that this is just a portion of a circle. So this part is called a sector. That part is called a sector. And therefore, if we know the area of the circle, we can also find the area of the sector. And using related knowledge we have learned, even in calculating the arc length, we can also get the area of a sector using the same premises that we used when we were calculating the area, the arc length. So we want to look at different sectors that we have in a circle, so that we are able to derive a relationship that will give us the area of a sector. We have the first one, we call it a quadrant. And we have said a quadrant is just basically a quarter of the area of a circle. Let's look at how it looks like. Let's see. This one is called a quadrant because it's just a quarter of the area of a circle. And how do we get it? We get the area of the full circle, then we divide by 4. This angle is 90 degrees. So area of a quadrant is given by a quarter of the area of a circle. But the formula for finding the area of a circle is pi r squared. But we want the quadrant, so it will be multiplied by a quarter. Which is pi r squared over 4. That is a quadrant. And we find that area like that. Let's go to the next one. Area of a semicircle is basically half the area of a circle. So if we get half the area of a semicircle, we have that one there. That is the center O. That is the radius. Equals to a half multiplied by pi r squared and we get pi r squared over 2 as the area of the semicircle. Let's go to the third obvious portions of a circle. Three-quarters of the area of a circle. This means we have 3 quarters, just from the word 3 of the quarters. So it's basically 3/4 of the area of a circle in a mathematical connotation. Class, this is what we are talking about. You can see that this part is removed, so the area we want is this. But we have said that it is 3/4 of the area of a circle. So you can see it is, from the definition, it is just 3/4 of the area of a circle. So you multiply area of a circle by 3/4, you will get area of 3/4. So you get 3 pi r squared over 4. That will give you 3/4 the area of a circle. Those are the obvious sectors of a circle that we can easily get when we are given such a question. But suppose now the portion of the circle we are given is not, it is not a quadrant, it is not a semicircle, neither is it 3/4. What do we do? Suppose it is not a semicircle, it is not a quadrant, nor is it 3/4 of a circle. Is it possible to find the area of such a portion? We say yes. Why? We use the basic premises which we have used in calculating the area of a quadrant, the area of a semicircle, the area of 3/4, to actually calculate the area of a portion of a circle given. And that portion given will depend on what we call the angle subtended at the center of the circle by that portion. So let's look at an example. Now, we have said that generally if the portion of the circle given is not a quadrant, semicircle, or 3/4 of a circle, we can still calculate the area of the sector if we know the angle subtended at the center of a circle. By inference, we know that the total angle in us, the sum of angles in a circle is 360 degrees. So the area of the circle will be a fraction of 360 degrees, because if we know the angle subtended at the center of the circle, it will be the angle subtended at the center of the circle over 360 degrees, then multiplied by the area of the circle. So example. Now, class, you can see that we have an angle subtended at the center of the circle, theta. By an arc length L. By an arc length L. So if this arc length L subtends this angle, it means that the area that it includes, it encloses is this particular area, and that area is known as the sector, area of a sector. So to get the area of this sector, it will be, we get the area of the whole triangle, circle, sorry. Then we multiply by the fraction of theta over 360 degrees. So area of the sector now is given by A is equal to theta over 360 multiplied by pi r squared, where pi r squared is the area of the circle. So area of a sector is given by that, where r is the radius of the circle and theta is the angle subtended at the center of a circle. So class, with that now, we are able to calculate any area of a sector and related questions to sectors and areas of circles. I want to end my lesson there, class. It has been an enjoyable morning. I've enjoyed teaching you. So when we meet next time, we look at examples on the application of area of sectors of circles. Thank you.